Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into functions today. Hi Hans, how's it going? I guess you are the first in chat. Yes, I guess you are first today. But how are you doing, Hans? How are you doing? How's everybody doing? It is Wednesday, so congratulate yourselves. You're already in the middle of the week. Soon the weekend will be coming up, and hopefully you will have some stuff that will basically entertain your mind as well as entertain your soul during those times of rest, hopefully. If you guys got to work the weekend, hopefully you guys won't have a tough time during the weekend rush. So, anyway, let's get into the pigeonhole principle. Now, I have heard of this, but I've never done any problems involving it, though. So, let's see. So, I think any definition we find, we're just going to basically just copy it, because I know I'm going to end up coming back to the book, like, a lot. There we go. Let's take this. What's the best part of your day so far, Hans? Pretty sure there's something. Whenever I ask that question, some people are like, I don't know, and I'm like, there's gotta be something. I mean, you woke up this morning, that's one thing. So, pigeonhole principle. Suppose A and B are finite sets, and f and a function f, A to B is any function. If the cardinality of A is greater than B, then the function is not ejective. If the cardinality of A is less than B, then the function is surjective. Okay? Sounds simple. Sounds simple, but probably when we apply it, it's going to be a little bit challenging. Listen to music? Yeah, hey, there you go. Listen to your favorite tunes. That's always going to be important. Let's see. I did read a little bit of this. Basically, they're giving us an example here. Let's see, okay. Let's see, proposition. If A is any set of 10 integers between 1 and 100, then there exist two different subsets, X in A. X is a subset of A, and Y is a subset of A, for which the sum of the elements in X equals to the sum of the elements in Y. Okay. To illustrate what this proposition is saying, consider the randoms. I tried to find it. I mean, did you create the pattern yourself, or did you just found the pattern somewhere? You could also... You created the pattern yourself? Okay. I mean, that's cool. I mean, it shows that you're clever. You can make, like, awesome puzzles. And plus, my Discord server is not that huge, so sometimes I'm not very active on it, so I'm probably partially to blame for, like, people not engaging with the problem, so apologies. Apologies. So we have 10 integers from 1 to 100. Notice there's... Alright. Okay, here's the proof. Suppose that A is from 1 to 100 and the cardinality of A is 10, as stated. Notice that if X is a subset of A, then X has no more than 10 elements, but each between 1 and 100. Therefore, the sum of all the elements of x is less than 100 times 10, which is just 1,000. Okay. So, where function of x is the sum of the elements in x, for example, equals 60 and 1/7. Alright. As the cardinality of the power set of A is equal to 2 times 10. Okay, so the cardinality in here is smaller than the cardinality of this. It follows from the Pigeonhole principle that f is injective, therefore... Okay. Sounds pretty self-explanatory, and this section is quite short, so maybe we can give it a try. See how we can implement our skills. And if nobody finds the pattern, I do have multiple hints I could give. Thank you for leaving that open for us, Hans. Appreciate it. Yeah, like that was actually a pretty good puzzle though, but I haven't figured it out yet. I was like trying to like match up numbers and stuff, and I was like, I feel like there's some sort of hint here, but like I haven't figured it out yet. So I think it's a clever puzzle. So I commend you on your ability to make such an awesome puzzle. Let's see, prove that if 6 integers are chosen at random, then at least 2 of them will have the same remainder when divided by 5. Oh, this one sounds like a challenging one. Okay, so maybe we should write the scratch work first. So scratch work. Okay, so let's say we have a set A that if 6 integers are chosen at random, so A is an element of big integers. Such that A's cardinality is equal to 6. And no, actually I should put not an element, but A is a subset of the integers, and is an element of A. So you prove that if 6 integers were chosen at random, then at least 2 of them will have the same remainder when divided by 5. Okay. So this one is a pretty abstract one. So we have A, which is a set of 6 elements that are elements of the integers. So we have an infinite amount of numbers to pick, but we can only put 6. So at least 2 of them. So if we imagine this, so put like actual numbers, like you have 1, 2, 3, 4, 5 or something. I want to actually like make it so that we have a random assortment of them. So let's imagine that we have a 1, a 2, a 3. Let's put a little I here. I is an element of the natural numbers. Or maybe I should put is an element from the set 1, 2, 6. At least 2 of them will have the same remainder as 5. So we have an output. So at least 2 of them Let's see, fun fact about me is that I get around 60 grams of protein daily just by drinking milk alone. Wow. Interesting. Now, is that a bad thing or a good thing? I would say it's good. Okay. As long as it's good for you, then that's fine. I have a major sweet tooth, so sometimes like I overeat. The weird thing is that whenever I'm at home, I can eat like probably a lot more than when I go out. Because whenever I go out, like whenever it's dinner time, when I see sweets on the menu, I'm like I instantly get like, I wouldn't say full, but I get close to it and I'm like, oh my gosh, dang. And they have like such good desserts here. And then I would ask like, what's the size of the dessert? And if it's small, then I get it. Or if it's like bubble tea, I probably just get bubble tea. But even bubble tea fills you up sometimes. Alright, so the question is that it's supposed to be 2, so it's in at least 2 of them. So just B1 and B2. That is 12 liters of milk a week. Wow. Thank you for actually doing the conversion. Actually, Hans, like you you did say that you're interested in math, and like, what other subjects are you interested in? Is it like, do you like literature? Do you also like history? Like, what is the thing? Programming? Okay, so I'm guessing you like dealing stuff with computers. Like, what code do you know so far? Like, do you know JavaScript? Do you know C++? Do you know Java? There's so many code languages there, like Python and all that stuff. I don't know any code, to be honest. I did take a course on C++ once, but then I got bored with it, and I was like, I passed the course, but I was like, I don't remember anything from that. Nothing yet learning currently. Oh, what type of code are you learning though? Are you just basically haven't started yet? Let's take a look at the examples of what they used. So far just block. Oh, okay. I gotcha. Did you create anything with that code? Usually the best part about code is when you actually create things with it. But I want to learn the text languages, but it takes time. Yeah, learning anything always takes time, which is why I'm putting so much energy and time into math. So, you know, it always takes a little time. There are at least 2 Texans with the same number of hairs. Let's see, the first we will use 2 facts. First, the population of Texas is more than 20 million. The second is the biological fact that every human head has fewer than 1 million hairs. Let A be a set of all Texans. Let B... Okay. Let the function A be... So some of the elements, okay. Okay, so far, if the way we set this up, A's cardinality is greater than B's cardinality, meaning that this is not injective, right? Yeah, it's not injective. But we also need the function, so because we have a function that's supposed to be now I have to think about the what is it, the division, the division definition, fundamentals counting. I think it's, let's see, multiplication principle, division. I need like division. I think it's in here. If not, then I have to go back. Okay, pre-orientation, no. Let's see. I've made my own 2D platformer from scratch. Nice. But I used a tutorial for most of it, so I can't really call it my own. I get that. That's the same thing when I solve math, when I try to solve math problems and then I had to look at the example, and it helps me figure out what to do. I kind of feel like, oh, I didn't fully solve that problem. So I get what I get that feeling. lot of my programming has been okay. Interesting. Yeah, like when I was in school, we weren't programming games like at a young age. Like when my nephew basically told me that he programmed a game like during middle school, I was like, oh dang, everyone's getting so advanced now. I think with AI soon you won't even need to program anymore. You won't even need to code. Okay, this is the power set. Middle school too. Oh, okay, I see. Pretty sure I saw like the definition for division, like the division for here we go, division algorithm. I always have a problem finding you. So you're always in the set that are number systems. Okay, so I have to keep in mind. I have to keep in mind that that's where you are. I always look for this definition every single time I need like something to explain something. So the function of I, where I is any number, is equal to. Let's see, given the integers a and b, let's see, b is greater than 0. There exists a unique integer q and r for which. Okay, so now we gotta figure out how to write this the correct way. Or we can do it the modular arithmetic way. So now I gotta look for the modular arithmetic way to like write this. Let's see. I think they do go over modular arithmetic here. Yeah, here we go. They don't go over it before, right? Yeah, oh yeah, they do. Over here. We got partitions. You still need people to understand code. AI doesn't have the same creativity as humans yet. Not yet, yeah. I get that. But I remember those times like universities would tell people like, oh, you should learn how to code. And then like now that because like now that like basically technology is catching up with human intelligence, like a lot of people are like, oh yeah, about that. I'm not saying people should stop learning code if they want to. I'm basically saying like if people like don't want to endure the struggle of coding, then yeah, it's not a big deal if you don't learn it. It's like when you tell people you don't really need to know like higher levels of mathematics to live a good life, right? I mean, I just like learning because I just want to nurture my curiosity. My headphones disconnected right after I said yeah. Oh, okay. So at least 2 of them will have the same remainder when divided by 5. So don't know if we have enough information to write a proof yet. That's the one thing. Do you think giving another number would make the pattern easier to find? I mean, usually, like, with patterns, more data is valuable. So it depends on you. If you want to, like, go in our Discord server and just add more numbers, then that's perfectly fine. Because I posted the problem on the assignments from streams. So if you would like to add more numbers to it, you're more than happy to do so. But it's primarily up to you. If you feel like that's enough numbers to give like the person who's trying to solve the puzzle like more ideas on how to solve it, then you probably don't have to add them. Or I could just say that the numbers I mentioned are in the middle of a pattern, not the start and or the end. I think that might be giving too much away though. But then again, like, you know, like I think like if people want to take on the puzzle, they can basically just take a look and like see if they want to test it out, because like when you give too many hints, people get a little bit like they're in like the solving mood and it's like, no, I want to solve it. So they try not to look at the hint or the solution. So it depends on like you. I feel like if anyone wants to engage with the puzzle, they'll get engaged with it. Okay, so the one thing I'm wondering about is the function, because I feel like the function might be okay, so let's just start writing what we know. So suppose A is a subset of the integers. Let's say that, yeah, of the integers. And the cardinality of A is equal to 6. Oh, hey FizzBuzz, how's it going? If you guys are not familiar with FizzBuzz, FizzBuzz is another awesome math streamer, as well as I think you also do like computers and physics, right? So I will give you a shout out, FizzBuzz. If you're not familiar with FizzBuzz, and if you like physics, math, or computers, check out his stuff. There we go. What's the best part of your day so far, FizzBuzz? Yeah, right now I'm just thinking about how to write this proof. It's the first proof of the day. I mean, technically two of them. Two, see. Day is that it's much cooler than yesterday. Yeah, actually we're like getting a little rain on my end, so I usually like when it rains. I don't like walking in it, but I like watching it from inside. It's not like a heavy rain, it was just like probably like a shower a little bit. Sorry about that, guys. Like, I got a text message on my phone and I was like trying to communicate something with like a couple of my friends in a group chat. Got a bit distracted, but we're back. So So now I gotta think about what is the function that we can use. Because it says here in the problem, prove that if 6 integers are chosen at random, then at least 2 of them will have the same remainder when divided by 5. So now we have to create the function in which we get the remainder. So times q. I mean, we can use the division algorithm and just solve it for r. So then it would be a minus q of b. So instead of b, we can replace that with 5. I mean q, we can replace that with 5. So now I gotta figure out how to write this. Therefore, there is a set x, which is a subset of A, in which x cannot have no more than 6 elements, each between 1 and z. Now I have to define what A and B are. So I don't want to put too many variables. That's the thing I'm concerned about, because we have Z that represents like an element of the integers. Well, actually, technically, we have 6 elements here, so. Hey, Famish. What's the best part of your day so far, Famish? I'm feeling a little sick, but trying to finish my entire programming course by Sunday, and then I have psychology and world civilization to read. Oh, dang. That's a lot. Hopefully you get all that stuff done. I feel like I'm sort of getting a little lost. Like, I feel like I know what needs to be said. The problem is that how to write it down. This one's 12.3. I only have 10 more chapters to read, so not a whole ton. But that's still a lot, though. Unless you can skim a majority of it and just take like short like notes of the overall major points. Here we go. Can you write that right? Okay, so we did set up this part right. Okay, this is the partition of into 5 sets. 6 integers are picked up at random by the Pigeonhole principle. At least 2 will be in the same set. However, each corresponds to the remainder of a number after being divided by 5. Of all those integers, that leaves a remainder of 1 after being divided by 5. I mean, that's an interesting way to write the proof. Let's see, this partition of... Now I have to think about what a definition of a partition is. Here we go, partition. A partition of a set is a set of a non-empty subset of A, such that the union of all the subsets equals A, and the intersection of any of the 2 subsets is equal to the empty set. Yeah, I'm just reading first and highlight the major points and then going back to take notes and translate the pseudocode into Java. Oh, okay, I see. I think with partitions you begin to learn about like why I think like it helps you like create a proof like that shows that subtraction. You can create like the arithmetic of subtraction. But I think it works with any type of form of arithmetic. Okay, prove A is a natural number, there exists two. For some reason, something in my brain is telling me that I should learn. I should probably try to practice like other problems, like computational math. So I think it's because like I'm getting distracted by so many things. But that's how scatterbrained I am whenever I'm studying on my own. It's just like, maybe I've been putting off like regular calculus for way too long. For some reason, I want to read about curves. Is it the same chapter? Lines and curves in space. Because I remember I read somewhere in this book they defined what a curve is. Like a mathematical definition of a curve. Length of curves. I think this is the chapter. The arc length. Curvature and normal vectors. Here we go, curvature. That's what I was looking for. Okay, curvature. Let R be described as a smooth, as a smooth I don't know why I said firm. Let R describe a smooth parameterized curve if S denotes the arc length and T is the the derivative of R over the magnitude of the derivative of R is the unit vector. The curvature is okay. I always forget how to read this letter. Oh, kappa. Okay, kappa. At least the author state that. Okay. Because sometimes, like with math textbooks, I always forget that sometimes they expect you to know Greek, and then you forget what the letters are. Like, I mean, alpha and beta and gamma I've gotten used to, but the other ones like omega and like omega I kind of remember, and then like I get mixed up between phi and phi. Note that is a non-negative scalar function. Okay. So we have to get the unit vector of the function here and the curvature formula. Okay, so yeah, sometimes like when I study, I get pretty scatterbrained that I'm like, oh, I'm getting bored with proofs. Let's do something else. I don't know if that's bad or good, to be honest with you. like a lot of my friends have short attention spans, and sometimes I feel like maybe I do too. Okay, the line zero curvature, so consider the line. Let's try this example. The thing about calculation-based math is like sometimes when you're given like a lot of stuff, like at least some info, you feel as if you can immediately put it into practice, but sometimes you just have to like look at it first. So we have R, which is the vector okay, show that kappa is equal to 0 at all points in the line. So we have to take the derivative of it. So I'm guessing we're going to have to take the partial derivative of each one. No, I think we have to take the derivative to t, right? Yeah, because like meaning that it's by t, that means we're left with A, B, and C as a vector, and then with that we have to take the magnitude of A. This the vector A over A squared, it's B squared, C squared, and then B over so next we have to then we gotta do so R is equal to the derivative, so in that case, the curvature formula is, that's supposed to be kappa, it's not supposed to be K. That probably is not a great way to write it, but we'll do it that way. And then take the derivative of this, from t, it will literally be 0. That's how it's supposed to go. Yeah, because it's constant. So, okay, so we managed to figure that one out. Let's try example number 2. Let's see how that looks. Circles have constant curvature. Oh, okay. Consider circle. Okay, for where show that comes. Okay. So we have R of t, which is equal to R sine of t. So this is polar coordinates. So if you take the derivative of it by t, then you're left with negative sine of t and cosine of t. And then you have to take so that turns out to be r squared which in turn just equals r, well, just r. So in that case t is equal to r over cosine which turns out to be negative sine and cosine. Alright, so now we gotta take the derivative of t. So d of t over t, that would be negative cosine t, and negative sine of t. And then to calculate the curvature in t, or kappa t, then we have our r. Well, actually, it's supposed to be r sine now we got to do magnitude, so this would just be 1 at this case, yeah, because we multiply these two and then it would turn out to be 1. So there's 1 on here, and then this one is just purely r. So this one is supposed to be, so it's supposed to be, so then it's supposed to be the result of that, because it's equal to, so then I don't know. Why is it that I got 2 of these? Because I understand from this one we got this. But then we ended up getting another 1, so it would be 1 over r squared, which I'm not understanding why. Must have missed something. Yeah, we did this right. Did that. Oh, maybe I did an error here. Oh, oops. I guess like this, I mistakenly did this. Okay. So it's the same, it's just that I thought that this was equating to just this, but then I think this whole thing is supposed to be this whole thing. Okay, that makes sense. So in this side, what I should have done. Okay. Check what the... Okay, so now we got a quick check here. So we can try to do this. Alright, what is the curvature of the circle? Actually, I should just put like little arrows on top. I forgot to do that. Okay. Now, if we do this, then we'll be left with 3. Yeah, we'll be left with 3. And now, for T. Okay, so D of T is negative sine, and then negative cosine. So T is equal to times because it would just be equal to sine squared plus cosine squared, which is 1. And I think at the end of the book they show you, I mean not the end of the book, the end of the chapter. Yeah, there we go. Alright. But that was only the first section. Okay, now we're on to the next part, alternative curvature formula. Let's see, the second curvature formula, which pertains specifically to trajectory of objects, is easier to use in some cases. Okay. Just give me a moment, guys. I gotta like do some stuff on my end. Sorry, I was just like clearing up some things with my friends over our text chat, so I had to like deal with some things. So sorry to keep you guys waiting. Okay, the alternative curvature formula. Let's see. So it's showing the cross product. Interesting. So basically it's the cross product of velocity and acceleration over the magnitude of the velocity. Let's see where the derivation comes from actually. So that's the derivative. Okay. Oh, I think they're doing the product rule here. So I'm guessing because these are two vectors, they're basically doing like they have to do like vector multiplication. So that's an interesting way to derive curvature. have this alternative curvature formula. And now, let's see, use the alternative curvature formula to compute the, oh, okay. So I think we have all the tools we need, so let's just do this. Okay. So in order to do this one, what we need to do is that, oh, oops, forgot to activate my pen. So, 2t, and then, oh, we don't have any t's in here, so they're all 0. Okay. So that's the velocity. Now we gotta take the second derivative of this, which gives us 2, and then 0, 0, 0. So now we have to take the cross product of these. Well, actually, first we'll do the cross product. So this is A, and this is V. So then, I mean, it's all 0, so practically, I'm just writing this out so I don't get confused. It's just an old habit. So the first one is definitely going to be 0. So there's no I. And then plus, that will also be 0. And then the next one, so that's also 0. So technically this is all 0. So we don't have any curvature in this. Yeah, we don't have any curvature. Okay. Okay, so curvature of the parabola. Okay, I think this one's an interesting example. Let's see if we can do this one. Since it's right after they introduced the okay, find the curvature of the parabola. So I think we can do this both ways, but we'll do it the way we just learned, the alternative. So this one is 1, and A, and the next one will be 0, 2A. Then we have to take the cross product of both of these. So then 1, 2AT. Well, then again, this is 2 vectors. So I don't think we need to do that. So, because usually I know the cross product works well with 3-dimensional vectors, but it's not great for everything else. So I think now we can probably do the curvature the old-fashioned way, which is Ooh. D of T. Yeah, this one's not going to be pretty because I just saw what we have to deal with. Maybe it would be easier if we did it the other way. Yeah, probably it might be easier to do it the other way around, because if we do take the derivative here, it's just going to give us more of a headache. So if we did take the cross product, then that would equal 2a. And then for but the weird thing is that for this curvature, it would still have like a t in it. Well, actually, I guess that's how it is. Very interesting. I thought they would like have you like try to, because since it's a scalar, I'm guessing like as time passes, it just basically just becomes a number. It's not really like being a vector anywhere. Okay, so I guess that's how it'd be, I guess. But I think what's cool is that when it comes to like curvature, like it's just cool that you can actually just calculate it like in a small way like this. Just basically like a little number, like basically it with a formula like this. I find it very, very kind of assuring actually. I can't really explain it. Oh, this is interesting. So, parabola, flattened curvature, maximum curvature. That is pretty interesting. And I think it would be the same the way we did this. Alright, principle of unit normal vectors. We're familiar with unit vectors, right guys? I think we are. If anyone needs me to explain, I'll try the best I can. If you want me to try to explain to you guys in chat, just let me know. D of ds. So practice the. So basically, they just want us to take the derivative. And then divide it. Oh, okay, yeah, they are doing the normal vector like type of setup. And the oh, okay, so the curvature is like it's like 1 over the curvature to get like the normal unit vector of a curve. That is pretty interesting. I wonder if like this curvature equation, like since we're learning a lot about curvature in this chapter, I wonder if it has anything to do with Einstein's theory of general relativity. Like probably they don't do it, like maybe it's not as simple as this, but maybe like some of these ideas play a part in it. I wonder. So we can copy this. This is the definition. Then probably copy this because it's a theorem. Usually theorems give us bigger ideas. Let's see, let R describe the smooth parameterized curve and the principal unit normal vector at a point P on the curve at which curvature is equal to 0, is not equal to 0. Oh yeah, because it's a fraction in this case. I wonder what the math proof was behind this one. Probably have to look that up, like probably like outside of stream. Let's see the properties of the principal unit normal vector. Let R describe a smooth parameterized curve with the unit vector t and a principal unit vector n. T and n are orthogonal at all points of the curve. That is, t of t dot product t n of t is equal to 0 at all points where n is defined. Okay. The principal unit normal vector points to the inside of the curve and the in direction that the curve is turning. Okay. Oh, they even show you the proof. Let's see, as unit vector t has constant length, therefore, by theorem 12.11, 12.10. I guess it's in the previous chapter here. 12.8. Wow, it's all the way back here. Here it is. Motion with constant. Let R describe a path in which is constant the motion on a circle or sphere centered at the origin. Then R dot, which means that the position R. So maybe we can just copy this definition too. Might give us some ideas like further down. Chapter I was on, or what section I should say. Okay, it was this one. Okay. Here we go. Almost lost my place here. Therefore, the theorems. We motivate, but do not prove this fact. Recall. Okay. Therefore, the points in the approximate direction when. Okay. Let's see. Consider the parabola. Does the principal point in the negative? Oh, okay. So I think this one would be probably a fun problem to do. And I think probably after we finish this one, I probably will end stream after this. So this will probably be the last problem of the day. So we got. So it's basically the derivative. T is basically the vector over its magnitude. So it's 1 times 4t squared. Which leaves us with this formula, we have to take the magnitude of that, so the magnitude of this would be this. Also have to take the derivative of this. I don't feel like writing the derivative out because that seems like it's going to be a ton to do. So does a point, does the principal unit vector technically, if you just take the cross product of, let's see. I mean, yeah, given the way this looks, this is like negative y here. Okay. I guess that's the reason why, because this one. Alright. Well, guys, sorry for like the distractions and like my brain is just like basically going all over the place today. Like so many things that are like boggling my mind. So I think it's like that's a good time to basically stop stream. But hopefully you guys were okay with us just basically shifting gears from like doing the pigeonhole principle proofs to doing curvature like example problems. But I think the curvature ones were a bit interesting to tackle because it kind of like gives me like a little bit more reassurance that I can do these things, like these type of things, like just doing base calculations or just doing like mathematical techniques. So I feel like it was like kind of like a good refresher to go into just purely just doing like just calculation base, because like I think with proof base it like takes a lot more time and a lot more energy for me to solve. But these, like, it feels like, oh, here's the formula, and just basically see how you can apply it to a problem here. And, you know, and I think that's the thing that sometimes I'm so used to with math. So kind of felt like I was exercising like a new part of my muscles, but at the same time it's like something that I got used to, like with just, I guess, because of school and like other stuff. But yeah, I think that will conclude it for today's stream, guys. I will see you guys next week. For those of you who are watching this on YouTube Live, if you like math or physics and you need a study stream to keep yourself productive while you're in front of the computer, consider hitting the subscribe button in addition to dropping a like and a comment down below. In addition, if you're watching this on Twitch, thank you for watching on Twitch, guys. Consider dropping a follow if you like math or physics, or you just need a study stream to keep yourself productive during your study time, because I know school is already started and probably some of you guys are just maybe just studying and you need someone to like be a study buddy during that time. So yeah, so thanks for joining us today, guys. I will put all the description, I'll put the Discord in the description down below, in addition to a link to my video game channel as well, my Uncle Talks channel. Okay, so that will do it for today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So see you guys next week. So take care, guys. Bye-bye.